In order to understand how a dielectric or an insulating material will affect the capacitance of a device, we need to know and understand the concept of a dipole, an electric dipole. So an electric dipole, basically you have two charges. One is plus Q, one is minus Q, the same magnitude but opposite in sign, separated by some distance d. If you take this dipole and you put it in an electric field, what will happen when you put it in the electric field? Well, assuming the distance stays the same, assume you have a rigid rod, for instance, connecting the two charges. This charge will experience a force to the right. This charge will experience a force to the left because it's negative. And the dipole will then tend to rotate. So, for instance, let's say you have a polar molecule. A polar molecule means that when the electric field is zero, the molecule is already polar, meaning that there's a separation between a positive and negative charge. You put this polar molecule in an electric field, in a region where the electric field is not zero, what will happen to this dipole? It will orient itself along the electric field direction. As we showed, when you put the dipole in the electric field, it will rotate until the positive charge points in the direction of the electric field and the negative charge points opposite to it. An example of a polar molecule, a molecule that's already has a separation between positive and negative charge without applying an electric field, is the water molecule. H2O, the two H atoms have extra positive charge on them, and the O has a bit of extra negative charge on it. If you look along the line joining the two, along this central axis, the center of positive charge is somewhere here and the center of negative charge is somewhere here. So there's a shift in the center of positive and negative charge. So that means that this is already a polar molecule without applying an electric field. Now when you put this polar molecule in an electric field, what will happen? Obviously the positive charges want to go to the right and the negative charge wants to go to the left. So again, this molecule will orient itself until it's in this orientation, where the center of positive charge is along the direction of the electric field and the center of negative charge is opposite the electric field. Okay, what will happen if you put a non-polar molecule, so in a region where there's no electric field? A non-polar molecule means that there's no separation between the positive and negative charge. The center of positive charge and the center of negative charge, they're at the same point. So the molecule is symmetric, for instance, like this. So when there's no electric field, it's completely symmetric. What happens when you put this molecule in an electric field? Well, the negative charge can't run away and go somewhere else in space, but there's going to be some shift between the positive and negative charge. The molecule will elongate a little bit. So the positive will be a bit elongated towards the electric field, the negative charge will be a little bit elongated away from the electric field. So the effect is basically the same. Whether the molecule is polar initially or non-polar initially, when these molecules are existing in an electric field, the net effect is the same. The net effect is that the positive charge and negative charge will be aligned along the electric field direction, with the positive charge toward the field and the negative charge away from the field. This is the summary of what we wanted to discuss in these slides.